10 functions of autotransformer you don't know about. Autotransformers are a type of electrical transformer that have a single winding with multiple taps instead of two separate windings like traditional transformers. They are often used to step up or step down voltage levels in electrical systems and offer several advantages such as size and cost reduction. Here are 10 functions of autotransformers. Voltage regulation is the process of maintaining a stable and consistent voltage level within an electrical system, despite variations in the input voltage or changes in the load. This is a crucial function in electrical power systems, as many devices and equipment rely on a specific voltage level to operate effectively and safely. Voltage regulation can be achieved through various methods and devices, including transformers, voltage regulators, and voltage stabilizers. Here's a more detailed explanation of voltage regulation. Maintaining consistency, voltage regulation ensures that the output voltage remains close to a specified reference value, typically the nominal voltage of the electrical system. This helps to prevent voltage levels from exceeding safe operating limits or dropping below the minimum required for equipment to function correctly. Load variation. Electrical systems experience changes in load, which can lead to voltage fluctuations. For example, during peak demand, the load on the system may increase, causing a drop in voltage. Voltage regulation helps to counteract these fluctuations by adjusting the voltage as needed to maintain stability. Input voltage variations. The input voltage to a system can also vary due to factors like fluctuations in the supply from the power grid or the use of renewable energy sources. Voltage regulation devices can compensate for these input variations to ensure a consistent output voltage. Protection of equipment. Many electrical and electronic devices are sensitive to voltage fluctuations. Voltage regulation helps protect this equipment from damage, as overvoltage or undervoltage can lead to premature wear, malfunctions, or complete failure. Improved power quality. Voltage regulation contributes to the overall quality of the power supply, reducing voltage sags, swells, and harmonics, which can negatively affect the performance of sensitive equipment. Energy efficiency. Maintaining a stable voltage level can enhance the efficiency of electrical equipment and reduce energy consumption, as some devices may operate less efficiently at higher or lower voltages. Voltage regulation can be achieved through various means, including the use of voltage regulators, transformers, both autotransformers and isolation transformers, and electronic devices like voltage stabilizers or automatic voltage regulators, AVRs. These devices can automatically adjust the output voltage to compensate for variations in the input or load, ensuring a stable and reliable power supply in electrical systems. Voltage transformation is the process of changing the voltage level of an electrical supply from one value to another, typically either stepping it up to a higher voltage or stepping it down to a lower voltage. This transformation is an essential function in electrical power systems and is typically accomplished using transformers. Here's a more detailed explanation of voltage transformation. Stepping up voltage. Voltage boosting. Voltage transformation involves increasing the voltage level from a lower value to a higher value. This is known as stepping up voltage. This process is essential for long-distance power transmission because higher voltages reduce energy loss during transmission and distribution. It's also used in various applications, such as in power generation, where generators produce electricity at a relatively low voltage which needs to be stepped up before transmission. Stepping down voltage. Voltage reduction. Voltage transformation can also reduce the voltage level from a higher value to a lower value. This is known as stepping down voltage. It is commonly used in power distribution systems to bring high voltage levels down to a level that is safe and suitable for residential, commercial, and industrial use. Transformers near the point of use then further reduce the voltage to a level compatible with specific equipment and appliances. Maintaining power transmission efficiency. Stepping up voltage for long-distance transmission reduces the current in the power lines, which in turn reduces energy losses due to electrical resistance. Lower current results in lower I superscript 2 or losses, where I represents current and R represents the resistance of the transmission lines. This is the fundamental principle behind the use of high-voltage transmission lines. Safety, stepping down voltage for use in homes and businesses ensures that electrical systems are safe for humans and equipment. High voltages can be dangerous and are unsuitable for most appliances and devices. Compatibility, different electrical equipment and appliances require specific voltage levels for safe and efficient operation. Voltage transformation helps ensure that the supplied voltage matches the requirements of the connected devices. Transformers, including both step-up and step-down transformers, are the primary devices used to achieve voltage transformation. These transformers consist of two coils of wire wound around a common iron core. By varying the number of turns in the primary and secondary coils, transformers can step up or step down voltage levels while maintaining the power balance, i.e., voltage times current, between the primary and secondary sides. This makes them essential components in electrical distribution systems, allowing electricity to be generated, transmitted, and distributed efficiently and safely. Impedance matching is a crucial concept in electrical and electronic systems, particularly in the field of RF, radio frequency, and high-frequency electronics. It involves the adjustment of the impedance of a device or a network to ensure maximum power transfer between the source and the load. Impedance matching is essential for efficient energy transfer and minimizing signal reflections. Here's a more detailed explanation of impedance matching. Impedance definition: impedance, represented by the symbol Z, is a complex quantity that encompasses both resistance, R, and reactance, X. It is a measure of the opposition to the flow of alternating current, AC, in a circuit. Source and load impedance: in electrical and electronic circuits, you often have a source, e.g., a signal generator, and a load, e.g., an antenna, amplifier, or transmission line. Each of these components has an impedance associated with it. Impedance mismatch occurs when the impedance of the source does not match the impedance of the load. Maximizing power transfer: impedance matching is primarily about maximizing power transfer. When the source impedance matches the load impedance, the power is efficiently transferred from the source to the load, with minimal reflections. This is known as the maximum power transfer theorem. Minimizing signal reflections: when there is an impedance mismatch, part of the signal power is reflected back to the source. This can lead to signal loss, degradation, and interference in electronic systems. Impedance matching reduces these reflections. Frequency-dependent impedance matching is especially critical at high frequencies, such as in RF and microwave systems, where reflections and losses can have a significant impact on signal quality. Components for impedance matching: various components and techniques are used for impedance matching, including matching transformers. These are devices that have different windings on the primary and secondary sides to adjust the impedance. Transmission lines. Transmission lines can be used to create specific impedance transformations. Matching networks. These are networks of passive components like resistors, inductors, and capacitors that are designed to achieve impedance matching. Applications. Impedance matching is used in a wide range of applications, including RF and microwave communications, antenna design, audio systems, and high-frequency electronics. It is essential in cases where efficient power transfer and signal fidelity are critical. Smith chart. Engineers often use a graphical tool called the Smith chart to analyze and design impedance matching networks. The Smith chart helps visualize impedance transformations and is a valuable tool in RF engineering. Impedance matching ensures that electrical and electronic systems function efficiently and effectively by minimizing signal reflections, optimizing power transfer, and improving overall system performance, particularly at high frequencies. Overcurrent protection is a vital aspect of electrical and electronic systems that involves safeguarding these systems against excessive current levels, which can lead to overheating, damage, or even catastrophic failures. Overcurrent can occur due to various reasons, including short circuits, overloads, and faults in the electrical network. Here's a more detailed explanation of overcurrent protection. Types of overcurrent. Overload. An overload occurs when a circuit carries a current higher than its intended or rated capacity for an extended period. It might be caused by connecting too many devices to a circuit, operating equipment beyond its specified limits, or an increase in load over time. Short circuit. A short circuit is a direct path between 2 points in a circuit with very low or zero resistance. It results in an extremely high current flow and poses an immediate threat to the safety of the system. Ground fault. A ground fault occurs when an unintended electrical connection between a live conductor and a ground, earth, occurs. Ground faults can lead to overcurrent conditions and pose electrical safety risks. Purpose of overcurrent protection. Equipment protection. Overcurrent protection devices, such as fuses and circuit breakers, are primarily designed to protect electrical equipment and devices from damage caused by excessive current. They prevent overheating, which can lead to component failure, fires, or even electrical hazards. Fire prevention. Overcurrent protection is crucial for preventing fires that can result from overheating caused by excessive current. When an overcurrent condition is detected, the protection device interrupts the circuit to mitigate the risk of a fire. Safety. Overcurrent protection ensures the safety of people working with or around electrical equipment. In the case of a short circuit or ground fault, the protection device quickly disconnects the circuit, reducing the risk of electric shock and other hazards. Overcurrent protection devices. Fuses. Fuses are overcurrent protection devices that consist of a thin wire or strip that melts when exposed to excessive current. This interruption of the circuit prevents further current flow. Fuses are commonly used in both residential and industrial applications. Circuit breakers. Circuit breakers are electromechanical devices that can be manually or automatically reset after an overcurrent event. They provide more convenience compared to fuses, as they can be reset without the need to replace a physical element. Relays. Electromagnetic relays are used in many systems to detect overcurrent conditions and trip a circuit breaker or disconnect switch in response to the fault. Ground fault circuit interrupters, GFCIs. GFCIs are specialized devices used to protect against ground faults, which are a type of overcurrent condition. They are commonly used in outlets near water sources, such as kitchens and bathrooms. Selectivity and coordination. In complex electrical systems, it's essential to achieve selectivity and coordination of overcurrent protection devices. This means that the device closest to the fault should operate before upstream devices to minimize the impact on system operation and minimize downtime. Overcurrent protection is a fundamental aspect of electrical safety and system reliability. Implementing the right protection devices and practices is essential to ensure that electrical systems operate safely and efficiently, protecting both equipment and personnel. Phase shifting is a process in which the phase, timing, of an alternating current AC signal is intentionally changed or shifted relative to another AC signal. It is a common operation in various applications, particularly in electronics, power systems, and signal processing. Here's a more detailed explanation of phase shifting. Phase definition. Phase refers to the position of an AC waveform at a specific point in time, often measured in degrees or radians relative to a reference point, such as the peak or zero crossing of the waveform. In a sinusoidal waveform, a phase shift represents a time delay or advancement of the waveform. Purpose of phase shifting. Control and regulation. Phase shifting is used in power systems to control and regulate the flow of power, adjust the voltage or current waveform, and improve the power factor. It can help balance loads and stabilize the grid. Signal processing. In signal processing applications, phase shifting can be used to align or synchronize signals, filter out certain frequencies, and adjust the timing of signals to achieve specific effects. Frequency control. Phase shifting is essential in frequency converters and oscillators to generate and control different frequencies. Modulation. Phase shifting is a fundamental concept in modulation techniques such as amplitude modulation, AM, and frequency modulation, FM, used in radio communications. Antenna arrays. In antenna arrays and phased array radar systems, phase shifting is used to control the direction and beamforming of the transmitted or received signals. Methods of phase shifting. Passive phase shifters. Passive phase shifters typically use passive components like resistors, capacitors, and inductors to introduce phase shifts. These components can create phase differences, but the amount of shift is often fixed. Active phase shifters. Active phase shifters use active electronic components like operational amplifiers or digital signal processors to create variable and controlled phase shifts. Transformers. In some power applications, phase-shifting transformers, which have multiple windings and can be tapped at different points, are used to introduce phase shifts between the primary and secondary windings. Digital phase shifters. Digital phase shifters, commonly used in communication systems, use digital signal processing techniques to adjust the phase of a signal in a precise and controllable manner. Applications: power system control. Phase-shifting transformers and phase angle regulators are used to control power flow and voltage regulation in electrical grids. Radio and wireless communication. In radio communication systems, phase shifting is used in modulation, demodulation, and beamforming to control signal direction and frequency. Radar systems. Phased array radar systems use phase shifting to steer radar beams electronically in real time, allowing for rapid target tracking. Audio processing. In audio systems, phase shifting can be used for effects like phasing and flanging, creating unique sound textures. Phase shifting plays a crucial role in various engineering and technological applications, allowing for precise control of AC signals' timing and phase relationships, which is essential for optimizing system performance and functionality. Voltage stabilization, also known as voltage regulation, refers to the process of maintaining a consistent and stable voltage level within an electrical system, particularly when dealing with fluctuations and variations in the power supply voltage. The goal of voltage stabilization is to ensure that electrical equipment and devices receive a steady and reliable voltage, which is crucial for their proper operation. Here's a more detailed explanation of voltage stabilization. Voltage variations. Electrical grids and power sources can experience voltage fluctuations due to factors such as varying loads, changes in generation, and disturbances on the power distribution network. These fluctuations can result in voltage sags, low voltage, or voltage swells, high voltage, which can negatively impact connected equipment. Purpose of voltage stabilization: equipment protection. Voltage stabilization is essential for protecting sensitive electrical and electronic equipment from damage caused by voltage fluctuations. It prevents overvoltage and undervoltage conditions that can lead to equipment malfunctions or failure. Improved power quality. Maintaining a stable voltage level enhances the overall quality of the power supply. It reduces the risk of voltage-related issues like flickering lights, erratic equipment behavior, and voltage-sensitive equipment failures. Energy efficiency. Electrical equipment often operates most efficiently within a specific voltage range. Voltage stabilization helps keep the supplied voltage within this range, optimizing energy consumption and equipment performance. Safety. Voltage stabilization contributes to the safety of both electrical systems and personnel by preventing voltage-related hazards. Voltage stabilization devices. Voltage regulators. Automatic voltage regulators, AVRs, are devices that can automatically adjust the output voltage to compensate for variations in the input voltage. They use electronic or electromagnetic techniques to regulate voltage. Uninterruptible power supplies, UPS. Some UPS systems include voltage stabilization capabilities. They switch to battery power or use voltage correction circuits to maintain stable output voltage when the input voltage deviates from the desired level. Voltage stabilizers. Dedicated voltage stabilizers are designed to stabilize the voltage within a specified range, typically through the use of autotransformers or electronic control circuits. Applications: homes and businesses. Voltage stabilization is crucial for residential and commercial buildings to protect sensitive electronics, appliances, and lighting systems from voltage fluctuations. Industrial facilities. Manufacturing and industrial processes often rely on equipment that requires a stable power supply. Voltage stabilization is used to ensure uninterrupted and reliable operation in these environments. Data centers, where critical computer servers and networking equipment are housed, use voltage stabilization to prevent power-related disruptions and data loss. Medical facilities, hospitals and healthcare facilities require voltage stabilization to ensure that medical equipment operates reliably and safely. Telecommunications. Telecom infrastructure relies on voltage-stabilized power to maintain continuous communication services. Voltage stabilization is an important aspect of maintaining the reliability and performance of electrical systems. By ensuring a consistent and stable voltage supply, it helps prevent costly equipment failures and disruptions in various sectors, from residential and commercial settings to critical infrastructure and industrial facilities. Traction applications refer to the use of electric power to propel vehicles, typically those designed for transportation over rails or roadways. These applications are commonly found in the realm of public transportation, including trains, trams, subways, trolleybuses, and electric locomotives. Here's a more detailed explanation of traction applications. Electric locomotives. Electric locomotives are used to pull trains along railways. They are powered by overhead wires, catenary system, electrified third rails, or onboard batteries. Electric traction provides advantages like high torque at low speeds, reduced emissions, and improved energy efficiency compared to diesel locomotives. Trams and light rail systems. Trams, also known as streetcars or light rail vehicles, are often powered by overhead wires or a trackside power supply. They are commonly used in urban areas for public transportation, offering an efficient and environmentally friendly alternative to buses and cars. Subways and metro systems. Subways and metro systems in many cities around the world rely on electric traction to move passenger trains efficiently through tunnels and above-ground tracks. Electric power is delivered through electrified third rails, overhead wires, or a combination of both. Trolleybuses, or trackless trolleys, are public transportation vehicles that use overhead wires to draw electrical power for propulsion. They combine the flexibility of buses with the environmental benefits of electric traction. High-speed trains. High-speed rail systems use electric traction to achieve fast and efficient passenger transportation. The electrification of tracks allows for high-speed electric locomotives and multiple unit trains, reducing travel times and environmental impact. Freight trains. In addition to passenger trains, electric traction is used in some regions to power freight trains. Electric freight trains can offer better acceleration, reduced emissions, and increased efficiency compared to diesel counterparts. Urban transport. Electric buses and trolleybuses are increasingly being adopted for urban transportation as cities seek to reduce air pollution and greenhouse gas emissions. These vehicles use batteries, overhead wires, or inductive charging systems for power. Energy efficiency. Electric traction systems often offer greater energy efficiency and lower operating costs compared to internal combustion engine-based propulsion. They can recover energy during braking and provide more consistent performance. Reduced emissions. Electric traction systems are cleaner and produce fewer emissions than their fossil fuel counterparts, contributing to improved air quality and reduced greenhouse gas emissions in urban areas. Noise reduction. Electric traction systems tend to be quieter than diesel or gasoline engines, contributing to reduced noise pollution in urban environments. Traction applications are crucial for sustainable and efficient public transportation systems, offering an eco-friendly alternative to traditional combustion engine-powered vehicles. They play a significant role in reducing emissions, promoting energy efficiency, and improving the quality of transportation in cities around the world. Testing and calibration are essential processes in various industries and fields to ensure the accuracy, reliability, and functionality of equipment, instruments, and systems. These processes involve assessing the performance of devices, making necessary adjustments, and verifying their measurements against known standards. Here's a more detailed explanation of testing and calibration. Testing. Purpose. Testing is the process of evaluating the performance and functionality of a device or system to determine if it meets specified requirements, standards, or performance criteria. The primary goal is to identify any defects, deviations, or weaknesses. Types of testing. Functional testing verifies that the equipment performs its intended functions correctly. Performance testing evaluates the device's performance under various conditions, e.g., load, temperature, stress. Safety testing ensures that the equipment complies with safety standards and does not pose hazards to users. Environmental testing assesses how the device behaves in different environmental conditions, e.g., temperature, humidity, vibration. Reliability testing determines the device's durability and reliability over time. Software testing evaluates the functionality and quality of software applications. Industries testing is critical in various industries, including manufacturing, automotive, aerospace, electronics, telecommunications, healthcare, and more. It is particularly important in quality control and product development. Calibration. Purpose calibration is the process of comparing the measurements of a device or instrument against a known standard to ensure accuracy and traceability. It involves adjusting the device to bring its measurements in line with the standard. Types of calibration. Electrical calibration involves calibrating instruments like multimeters, oscilloscopes, and voltage meters. Mechanical calibration, calibrating tools and equipment such as torque wrenches and pressure gauges. Temperature calibration, calibrating temperature sensors, thermocouples, and ovens. Dimensional calibration ensures the accuracy of measuring tools like calipers, micrometers, and gauges. Flow calibration, calibration of flow meters and devices used to measure fluid flow rates. Accreditation, calibration laboratories are often accredited by relevant bodies to ensure that they follow recognized standards and provide traceable measurements. Industries, calibration is vital in industries where measurement accuracy is critical, such as manufacturing, healthcare, scientific research, and environmental monitoring. Quality assurance. Both testing and calibration contribute to quality assurance by ensuring that devices and systems produce accurate and reliable results. Compliance. Testing and calibration are essential for compliance with industry-specific standards, regulations, and quality management systems. Instrument maintenance. Regular calibration and testing are part of instrument maintenance to detect and address issues, prevent measurement errors, and extend the life of equipment. Safety. Accurate and reliable measurements contribute to safety, especially in applications where precise measurements are critical to prevent accidents or ensure the safety of personnel. In summary, testing and calibration are crucial processes that help maintain quality, safety, and accuracy in various industries. These processes ensure that devices and systems function correctly, produce reliable results, and comply with industry standards and regulations. They play a key role in product development, manufacturing, research, and many other fields. Energy transmission refers to the process of transmitting electrical energy from one location to another, typically over long distances. It is a fundamental part of the electrical power distribution system and is essential for ensuring that electricity generated at power plants can reach homes, businesses, and industrial facilities efficiently and reliably. Here's a more detailed explanation of energy transmission. Power generation, electrical energy is primarily generated at power plants, which can use various energy sources such as coal, natural gas, nuclear, hydroelectric, wind, solar, and more. These power plants convert these energy sources into electricity. Transmission lines, once electricity is generated, it needs to be transported from the power plant to various load centers, including cities, towns, and industrial regions. This is typically done through a network of transmission lines. High voltage. To minimize energy losses during transmission, electricity is transmitted at high voltage levels. High voltage reduces the current that flows through the transmission lines, and lower current results in lower I superscript 2 or losses, where I represents current, and R represents the resistance of the transmission lines. Step-up transformers. Before electricity is sent into the transmission lines, step-up transformers are used to increase the voltage. These transformers convert the electricity from the generator's output voltage to the higher voltage used for transmission. Transmission towers and lines. Electricity is transmitted through a network of transmission towers and power lines. These lines can be made of various materials, including aluminum and steel, and they are supported by tall transmission towers to maintain a safe distance from the ground. Long-distance transmission. Electrical energy can travel long distances over these transmission lines, sometimes spanning hundreds of miles, to reach its intended destination. Substations. Along the transmission route, substations are strategically located to control the flow of electricity, adjust voltage levels, and provide points for connecting and disconnecting various parts of the grid. Step-down transformers. Near the end of the transmission journey, step-down transformers are used to reduce the voltage back to levels that are safe for distribution to homes and businesses. Distribution networks. Once the voltage is reduced at substations, electricity enters the distribution network, which is a lower voltage system that supplies electricity to consumers. Distribution lines deliver power to homes, businesses, and other end users. Consumer use. Finally, electricity is utilized by consumers for various purposes, such as lighting, heating, cooling, operating appliances, and powering industrial machinery. Energy transmission is a vital part of the electrical grid, ensuring that electricity is efficiently transported over long distances and made available to consumers at the right voltage and frequency. Maintaining a reliable and efficient transmission system is crucial for providing a stable and uninterrupted power supply to meet the demands of modern society. Voltage conversion is the process of changing the voltage level of an electrical supply from one value to another. This conversion can involve stepping up, increasing the voltage, or stepping down, decreasing the voltage, depending on the requirements of a particular application. Voltage conversion is essential in various electrical and electronic systems to match the voltage levels of different components or devices. Here's a more detailed explanation of voltage conversion. Stepping up voltage. Voltage boosting. Voltage conversion can involve increasing the voltage level from a lower value to a higher value. This process is commonly referred to as stepping up voltage. It is achieved using devices such as transformers and voltage multipliers. Stepping up voltage is often necessary for long-distance power transmission to reduce energy losses due to lower current flow. Stepping down voltage. Voltage reduction. Voltage conversion can also involve reducing the voltage level from a higher value to a lower value. This is known as stepping down voltage. Devices like transformers and voltage regulators are used for stepping down voltage. This is important for safely supplying power to homes, businesses, and various electrical and electronic devices that operate at lower voltage levels. Transformers. Transformers are widely used for voltage conversion. They consist of primary and secondary windings and can be designed to have different turns ratios. By varying the number of turns on the primary and secondary sides, transformers can either step up or step down voltage levels while maintaining power balance, i.e., voltage times current, between the primary and secondary coils. Voltage regulators. Voltage regulators, such as automatic voltage regulators, AVRs, are used to maintain a stable and consistent output voltage regardless of fluctuations in the input voltage. They are often used in power supplies for sensitive electronic equipment, ensuring that the voltage remains within specified limits. Voltage converters/inverters. Voltage converters and inverters are used in electronics and electrical systems to change the voltage level for specific applications. Inverters, for example, convert DC, direct current, voltage to AC, alternating current, voltage, which is essential for various electronic devices and renewable energy systems like solar panels. Applications. Voltage conversion is essential in a wide range of applications, including power distribution, industrial machinery, electronics, and telecommunications. It is used to match the voltage requirements of different components and ensure the safe and efficient operation of electrical and electronic devices. Voltage conversion plays a crucial role in ensuring the compatibility and efficiency of electrical and electronic systems. By adjusting voltage levels to meet the specific needs of various devices and applications, voltage conversion enables the safe and reliable operation of a wide range of equipment and systems. It's important to note that autotransformers have some limitations, such as the lack of electrical isolation between the input and output, so they may not be suitable for all applications. Safety precautions and careful design considerations are necessary when using autotransformers to ensure the protection of equipment and personnel.